All right, I think that's probably safe to get started now. All right, so hey everybody, welcome to 16745, also known as Optimal Control and Reinforcement Learning. I wish we were sort of all together, but this is a flashback to a year ago, this exact time, doing this from home again. So we'll see how this goes. So I guess as just a quick logistical thing, definitely it's kind of hard to see I can't see all your faces at once on there's too many people. So it's hard to see the little hand raise thing. So if you've got a question or something to say, just for now, just unmute and speak up. And when you do that, I'd appreciate if you turn your camera on when you're talking, just so I'm not like staring into the void, and it'd be cool to see who's talking. If that becomes a problem with too many people trying to talk at the same time, then we'll figure something out with the hand raise thing or something like that. But for now, yeah, just unmute and then speak up, and that should be fine. A couple quick logistics things. I guess that was one. So next up is the course team who you'll be dealing with this semester. So I'm Zach. You can call me Zach. I'm an assistant professor in the Robotics Institute, and I lead the Robotic Exploration Lab, and our research is in optimal control, as you might expect. We do a lot of stuff with numerical methods and kind of very applied flavor of optimal control, which is basically what you're going to get in this class. So it should be fun. We can talk about our research too to some extent. If you guys are curious, don't hesitate to ask myself or any of the TAs. Brian Jackson, one of my PhD students, who was the TA for this course last year and did an awesome job, will be kind of the lead TA this time around again. So you guys are in good hands there. And Kevin Tracy, another one of my PhD students, took the course and is TAing it this time around. Actually, why don't you guys do a quick intro if you're on here? Sorry for that. Brian, do you want to say hi real quick? I'll let you guys introduce yourselves instead of me talking about you, which is weird. Oh, we can't hear you. How about we?
You can come. Yeah.
There you
go. You can hear me now.
Yeah.
Okay. Hey guys. My name is Brian. Like Zach said, I TA'd this course last year. I'm a fifth-year PhD student, and my research is in like applied numerical methods for optimal control. So yeah, here to help, and don't hesitate to reach out with any questions about anything class related.
Cool. And then Kevin's next up. Kevin, you want to say hey?
Sweet. Hey guys, Kevin. I'm a second-year PhD student. I do a lot of stuff pretty similar to Brian, optimal control for aerospace stuff. So if anyone wants to talk aerospace stuff, always let me know.
All right. And then Cheetah, who also took the class last year, is Cheetah, are you here? Maybe not. Okay, we'll skip Cheetah. And then last up, Alex, who also took the class last year and has been doing work in the lab with us. Want to say hi?
Hi, everybody. Yeah, I'm a second year master's student in mechanical engineering, and I work with Zach on like quad rotor control stuff.
All right, cool. So that's your course team for the semester, and don't hesitate to reach out to any of us anytime. Okay, so now I'm gonna kind of like lay out a little bit of kind of the state of the art in the field and some of the applications we're going to talk about later in the course. So this is sort of things you can look forward to and kind of the direction we're going to go and where we should get you to by the end of the semester. So first off, kind of what is optimal control for and what are people using it for right now? So originally, the earliest applications for optimal control, where a lot of it was originally developed, is in the aerospace field, which my lab still works in quite a bit. And originally this was developed for solving for rocket trajectories for launch vehicles, starting in kind of the 50s and 60s. And then for computing things like today, how to get to Mars, for example. So like designing the trajectories to fly a spacecraft from the Earth to Mars is done with the sort of trajectory optimization methods that we're going to talk about in the class. Specifically, this gets done with nonlinear trajectory optimization methods, often direct collocation. is kind of the method of choice for this stuff at places like JPL. So we'll talk about this a little bit, and this is sort of one of the current applications and historically one of the main drivers for a lot of the developments in this field. So some more sort of state-of-the-art, fun, current stuff that probably most of you are aware of is SpaceX landing rockets, some more aerospace stuff. Does anyone know how this gets done? Anyone who isn't one of the TAs or isn't in my lab? Does anyone have any thoughts? What sort of control methods are used to make this stuff happen? Land a rocket on a barge in the middle of the ocean. Pretty awesome. Has anyone followed this stuff at all? Nobody? No one has any thoughts? Take a guess. Someone take a guess.
I'll guess that it's some sort of model predictive control.
Yeah, so as a lot of kind of the stock stuff is these days, this is convex model predictive control with a lot of kind of secret sauce and robust low-level tracking control stuff. There's been actually a lot of progress in this sort of what's called the rocket soft landing problem in the last 10 or 15 years. There have been some major breakthroughs and some seminal results on how to do this with convex optimization, basically how to like sort of reformulate this rocket landing problem as a convex optimization problem. This is how we land on Mars and things like that, which is pretty cool. Someone said graduate student descent. It is thankfully not quite that bad. All right, so that's that. Okay, so another kind of current hot area, autonomous driving. Tesla here being kind of one of the big players in this and one of the interesting examples. So arguably the control problem here is not really the hard part. A lot of the kind of really tough challenges here are on the perception side of this problem. But anyone have any thoughts on how this gets done? Has anyone looked into this or did anyone work on driving stuff on this kind of end of things? Thoughts, comments, somebody say something. Help me out, guys.
Should be an adaptive controller.
So this stuff, not so much actually. So like kind of what the standard approach here is as again MPC for a lot of it, and then often some lower level linear tracking control stuff. So here the kind of the standard approach is to use a simplified dynamics model for the car. A lot of times people use what are called single track or bicycle models. And then it's kind of nonlinear MPC with constraints for collisions and obstacle avoidance and that kind of stuff is kind of the standard way of doing this. But there is some really exciting frontier research, some of which we've done in our lab on what's called kind of game theoretic control, which is where you try to reason about the behavior of the other drivers and how your control moves might interact with them and what they might do in response to you for things like lane merging and passing and stuff like this, which is pretty cool. So that's kind of interesting stuff in the driving realm. Okay, so some more stuff that's sort of state-of-the-art and cool. MIT Cheetah, a lot of people probably know about this and have seen this, and this is one of the more exciting and more dynamic legged robots. So this is once again model predictive control. A lot of tricks in here to make this into a linear model predictive control problem so that it can be solved online quickly. But some of the more state-of-the-art stuff is actually now venturing into nonlinear MPC here. So this is sort of, there's a linear MPC layer at the top, and then there's a bunch of kind of clever low-level control stuff going on so that you can treat this thing at the high level as a linear system, which it is most definitely not, right? It's a super nonlinear. So there's a bunch of secret sauce in there, but at the highest level, it is, again, a linear model predictive control problem or convex model predictive control problem that gets solved. And sort of maybe most exciting and kind of state of the art of all the stuff is everyone's seen this stuff, Boston Dynamics. This is, pretty much at the cutting edge of our field. And this stuff is, just incredible to look at what they can get these robots to do. Anyone have any thoughts on what these guys are doing? This is actually pretty speculative on my part as well. Like I have friends who work there and like know a little bit about what they're doing, and I have some good ideas, but these guys don't publish and don't talk about it. So we're all guessing. Does anyone have any thoughts on what these guys are doing?
do they do an offline trajectory optimization and then an online MPC?
Yeah,
Sort of match that?
Yeah, that's, as far as we know, and like, as far as I'll talk about, that's pretty much what's going on. So roughly speaking, what they're doing is an offline, very slow nonlinear trajectory optimization step to plan these motions. So they're like, with the full nonlinear dynamics of the robot, all the details in there, all the motor dynamics, et cetera, et cetera. So they're doing this like really kind of intense, high dimensional, big nonlinear optimization problem offline to figure out how to move the robot. And then online, they're doing some sort of convex model predictive control again, probably solving QPs again, using a bunch of simplifications and linearizations to track these pre-computed trajectories, along with some really clever stuff where they can sort of build a library of trajectories that they've computed offline and then select from them or switch between them online, sort of like template style, and then track them in kind of interesting ways. So that's sort of what we think they're doing. So yeah, so I see people writing in the chat. It's thanks for doing that. That's cool. Unfortunately, I can't see the chat with the PowerPoint on. When we switch over, it might be easier when I stop doing PowerPoint, but for now, yeah, just speak up. This is much closer to graduate student descent. Whoever said that, that's kind of true. Okay, cool. So Boston, these are kind of some, totally state of the art. This is, and by the way, we're going to explicitly go through most of these at the end of the class as kind of case study examples. So we'll get you pretty close, like right up to the frontier, hopefully, with some of this stuff. And hopefully you can leverage it. So some kind of like more forward-looking current research challenges, like what are we working on in our lab and what are others working on in this field, and where are kind of the really hard problems that we still don't know how to solve. Here's a handful. So one is dealing with contact in general. So legged locomotion would be a good example of this. You saw Cheetah, you saw Atlas, and also in manipulation tasks, right, where you're grasping and things like this. So anywhere where you make and break contact, things get really nasty and really complicated. And right now, pretty much every controller that deals with scenarios like that has some hacky heuristics in it to deal with what exactly goes around where you make and break contact. And there isn't really a good general, theoretically well-grounded set of tools for dealing with contact rigorously in control theory right now. So that's a big one that we do a lot of work on in the lab. Another one is, and we'll talk more about this, but really kind of bridging the gap between model-based control, kind of more classical stuff, and reinforcement learning ideas. And then, kind of very related to that, making RL more data efficient by incorporating prior knowledge, AKA incorporating more model-based control. So bridging the gaps between these things is kind of really interesting right now. There's a lot of work going on. That's a very hot area in general. From my perspective, RL and optimal control are really the same thing. They're kind of just historically existed in different communities or from different viewpoints or different departments, but they're really the same thing. And so now they're sort of starting to come together a little bit, which is kind of cool. So a couple more. Another one is safety guarantees for uncertain and/or nonlinear systems. So how can you actually guarantee that your thing's not going to face plant or blow up or crash? Given we have imperfect models of the world and bad things can happen. Can we give any guarantees, and what sort of guarantees can we give on performance and robustness and things like that? And then lastly, sort of related to this driving stuff and the game theory stuff, how do we deal with other possibly adversarial agents? So this shows up most prominently right now in autonomous driving as a huge deal. So these are a handful of like forward-looking things. We're happy to talk about all this stuff. We work on a bunch of this stuff in the lab. Okay, so that's kind of that story. So what are we doing here in this class specifically? So number one, we're going to be focused on optimization-based control techniques. So the title optimal control, I mean, that has a lot of sort of baggage or implications maybe attached to it. And what we mean by that is we're going to use optimization to do control. And that's sort of a very broad set of tools and ideas. We're going to focus very heavily on applications, robotics applications in particular, over theory. So this isn't really going to be a course where we are like proving theorems or deriving the Pontryagin minimum principle or things like that. We're mostly going to be focusing on coding up algorithms and really doing it. with an eye towards hopefully you guys being able to take this stuff and go apply it in your own research or in your own careers after this. We're going to have 4 kind of major homeworks over the course of the semester. They'll be coding assignments focused on implementing algorithms, trying stuff out, that kind of thing. So there'll be sort of Jupyter notebook based things, and do on GitHub and this kind of stuff. And then lastly, we're going to have a course project that you guys are going to work on in groups, nominally groups of 1 to 5. I think it's a better idea if you do this with somebody else. So if you're inclined to do it by yourself, I mean, that's okay. If you really want to, if you have something from your research that you want to do here, that's cool. But I think you'll have a better time doing it with a friend or two. And the idea here is to do something cool, do something interesting that interests you. Hopefully, if you're a graduate student, you can do something that's sort of directly related to your research, and hopefully get a kickstart, sort of jumpstart on a conference paper or something like that, and do something that's just totally relevant there. We don't want you to like spin your wheels on something random here. Do something that matters to you. Do something cool. Okay, and I should say as a disclaimer out the gate, this is definitely more of a optimal control class. It's definitely from an optimal control viewpoint as opposed to a reinforcement learning viewpoint. As I kind of alluded to before, from my perspective, these are really the same thing. And it's really just a matter of perspective and viewpoint. And like a lot of times, did you use a polynomial or a neural net in your function approximation is really what separates these things. So we're going to kind of try to look at this from a unified viewpoint, mostly deal with model-based stuff, but we'll also talk a bunch about what you do when you don't have good models, how you can use data-driven techniques, and sort of where all the connections are between optimal control and RL. And they're really kind of, it's a continuum, and they're really kind of in the same space generally. So hopefully we'll set you up with kind of a good baseline set of tools here and techniques and sort of knowledge base that you can use and apply in any of these settings. Okay, so logistical stuff. Lectures are on Zoom, as you all know, for now, because you're here. We hopefully will be back in person in a couple weeks, TBD. So more on that, I guess, in the next couple weeks. And I will record and post the lectures. This is getting recorded right now. I'll post them on YouTube in a playlist. And even when we go in person, I'll still record and post lectures. So let's see, I'll also post my notes. I'm going to write on a tablet, and those I'll PDF them and upload them to GitHub. I'll also do a lot of Jupyter notebooks and kind of demos in class where we play around with the code live. Hopefully it works most of the time. And so I'll post those Jupyter notebooks along with my kind of handwritten notes. We're going to use Piazza for like kind of course communication, real-time Q&A, etc. Hopefully all the course communication we can kind of just do with Piazza and avoid email. And I really don't want to use Canvas. I'm probably going to use it just for posting grades, but we're not going to like collect assignments on there or do any sort of communication really through Canvas at all. So definitely get on the Piazza site. We're going to use that for pretty much everything. We're going to use GitHub to collect assignments. I think that's about it. Yeah, so GitHub, we're going to use GitHub extensively, so need a GitHub account. I'm going to send out some kind of poll for office hours. So those are TBD. They'll be on Zoom for now, and we'll see in a couple of weeks, but we'll kind of dynamically adjust as we go for this stuff. And don't hesitate to reach out if you need to talk anytime. We're pretty flexible, and there's a bunch of us. Okay, so any questions about any of this stuff, any of this logistics stuff? And just unmute and speak up if you've got any questions. Anything I talked about so far? Questions, concerns, comments, thoughts? Okay, so onward then. So we have two kind of like to-dos for you guys. Assignment 0, we'll call it. So first is there's a course survey, Google form that's just me asking questions about like courses you've taken before, kind of background things to try to gauge where everyone's at and hopefully target the content a little bit. And stuff like that. And then we're the Piazza site, which we need everybody to join. So there's the links. This all get posted. I can probably put these in the chat as well. I'm gonna stop sharing my screen for a sec, and then I'm actually just gonna pull up the Piazza site and we can look at some stuff there. Okay, so let's try this. So a couple more things. Okay, so here's the Piazza site. And then right on the front page, here's kind of the survey link, the Zoom link, the syllabus, which we can take a quick look at. Just kind of go through, if anyone has any questions on this. So really what we want to look at here, so grading, it's going to basically be half project and then sort of 40% homework, meaning each homework's worth 10%. And then 10% participation, which is really like giving me wiggle room to bump people in the event that things are on the edge, stuff like that. Okay, so here's kind of what we're going to talk about. So today we're going to get, after we're done with all this upfront stuff, we're going to get into dynamics. And this is just kind of background on dynamical systems that you need to be able to do control. And hopefully that's mostly review. Next time we'll talk a bit more about stability and discrete time dynamics, which is how we get these into a computer. Then we're going to have a few lectures on just optimization in general. So kind of intro to optimization, and then a bunch of stuff about numerical optimization, how you actually solve these optimization problems with a computer, getting into how we deal with constraints, things like that. And then we'll get into sort of optimal control, which is kind of a special case of optimization in general. Some classic stuff, the Pontryagin minimum principle, shooting methods, LQR, sort of bread and butter stuff, Connet equations, dynamic programming. Then we're going to get into sort of convex model predictive control, a bunch of which is used all over the place right now. It's kind of one of the standard things to do. Then we're getting into sort of nonlinear trajectory optimization, how you solve those problems, a bunch more tweaks on top of that setup, direct methods, so co-location methods, things like that. Then we're going to talk about how to apply these methods specifically to systems with that have 3D rotations, which shows up all over the place in robotics. So anytime you have, a non-fixed base system, so legged robots that can rotate around all the way or do flips, aerial vehicles, drones, spacecraft, underwater vehicles, right? So anything that's not bolted to the world, like anything other than a classic manipulator arm. So we're going to talk a bunch about that stuff because it shows up in practice a ton, and it's sort of a pet peeve of mine that people kind of do it the wrong way a lot. So we'll teach you how to do it the right way. So we'll do a bunch of that stuff. Then we're going to get into some more robotic specific things. So we'll talk about contact systems that make and break contact, a la, legged robots and manipulators. How you do trajectory optimization for those systems. So how you do kind of the Cheetah, Boston Dynamics stuff. Then we'll talk a bit about data-driven methods and what to do when you don't have super good models. Then we'll talk about stochastic optimal control, so noisy sensors, things like this, and the LQG problem, which is a special case, which is kind of one of the classic bread and butter results in all of optimal control. So this is basically LQR plus a Kalman filter. Then we'll talk a little bit about robust control. So what if you have uncertainties on your model, and some methods for solving those problems. Then we'll do a little bit of a quick whirlwind tour of RL, hopefully, kind of with the same perspective and notation and stuff from the rest of the course. We'll do some, this stuff's RL as well. It's but this is sort of kind of maybe a broader survey of stuff. We did this last year, and I think it was a good thing to have. So kind of a practical tips and tricks session that shares a bunch of random things that you should know about, but that aren't necessarily theory things that are taught in most courses. And then last year we did these case studies, which I think were pretty cool. I'm open to adding more of these or having different ones, but last year we did the rocket landing problem. And then we did a bunch of stuff about driving and how the car stuff works, and then a bunch of stuff about walking systems and how kind of the quadruped humanoid stuff works. And then the last week is going to be for project presentations. So we'll kind of have you guys do lightning talks for the last couple lectures, and hopefully we can have some Q&A, and it'll be fun. So that's kind of the idea. The homeworks here, these will probably get spread out a little bit more, but it's kind of just generic for right now. And then I'm leaving kind of a good few weeks at the end for you guys to really kind of dig into the projects. That's the intent, at least. And the projects will be due like as late as I can do it, kind of at the end of finals time or whatever, just a few days before the deadline for me to hand in the grades. So I'll give you guys as much time as possible there. So you'll have a bunch of time after the presentation slots to keep working on the project right up. And on that note, you guys can all go read this, but just to give you a heads up, for the project, you'll have to do this kind of lightning talk thing, a couple of minutes. The last week, we won't expect you to have your full report done. At that point, you'll have another couple of weeks over the finals and everything to write it up. But the idea there is to basically make it look like a conference paper. So we're going to have you do kind of the standard ICRA IROS conference paper format. So it's a 6-page, 2-column IEEE format, kind of the standard thing. And so that's kind of the level we're looking for here is roughly 6 pages and, you know, kind of at the level of something, you know, that you could turn into a conference paper, hopefully. Okay, so that's, I think, kind of all the important highlights of what we're going to do in the class. Any questions about any of this stuff? Oh yeah, there's some other stuff to talk about. Okay, so late homework policy. So I'm going to just give you a budget of late days. I think we did 6 last time and that worked out okay. So you just have 6 late days you can use on any of the homeworks in any combination you want. Is there any other important things? I think that should be it. So we already talked about this. No textbook, but I'm going to post videos, notes, all that stuff posted. Yeah. Anybody have anything before we kind of think that's it for that for sure. Okay. Syllabus lecture notes will be on GitHub. Here's links. Last year's are up there too if you want to look at last year's. I'm going to make a YouTube channel playlist with all the videos. You can see last year's. And then the last thing is we have this Google form. So first off, yeah. We're not perfect. I make mistakes all the time. We can always make this better. So especially with weird remote kind of logistics, it's kind of weird. So if anybody has any feedback, I always want to hear it. Talk to me, talk to the TAs anytime about anything, content, logistics, concerns, whatever you got. Yeah, don't be afraid to speak up. And then if you don't want to sort of like talk face-to-face or Zoom or whatever, you can also do so anonymously. We have this Google form, which does not record your email address, not shared. I promise it's anonymous. And I just get a like totally anonymous email from this whenever you submit something with whatever you said. So yeah, I think that's it. So anyone has any questions, feel free to speak up while I switch over to actual stuff.
Yeah, I have a question.
Yep.
Are the homeworks auto-graded on GitHub?
So we have an auto grader thing, and we actually we try to be nice to you guys, and we actually post sort of like along with the assignments, we'll post sort of unit tests that will evaluate your answers, so you can check your answers before you turn it in, so that you'll know if you got it right, essentially. So there'll be like a set of tests that you can run yourself before you submit. And then when you submit, we'll run a different set of tests on it just to verify. But yeah, so there will be like some auto grading stuff. If you don't pass the test, we'll actually go look at it, you know, by hand and stuff like that, and for the grading. But yeah, you should. I mean, basically, it's set up such that like if you just put the time in, like you'll know if you did it right. If you give yourself enough time, you should be able to go through it. You know, make sure you're passing the test. If you're not passing the test, come talk to us in office hours. And figure it out, right? So I want you guys to succeed. We're not trying to trick you or anything like that. And as long as you kind of like put the time in, like, there's no reason you shouldn't be able to get perfect scores on the homeworks.
Cool, thanks.
Yeah.
I have a quick question.
Yeah.
Are there any readings for the class or like text or anything we should refer to?
So there's a bunch of optimal control textbooks. I can post some of those as references, as sort of general references. I'd say like I'm kind of taking a bit of a non-standard path through this. That's a lot more sort of like computational, implementation focused. And there aren't really a ton of good books on that, on a lot of the stuff we're going to do. But there definitely are some good general references, and I can definitely like post some material and try to like along with the lecture notes from each week, I can like definitely post some references to check out to sort of like go deeper and look for more. So that's a good one. I will take that as an action.
Cool, thanks.
Okay, yeah.
For the quick question for the homeworks, what programming languages
Oh yeah, that's
will we
a
mostly be
very
using?
good one. So Brian, would you mind taking that one real quick, and we'll use your stuff from last time? while I do this?
Sure. So yeah, we'll be using Julia in this class. For those of you who haven't used Julia, which is probably a good number of you, it's very similar to MATLAB, and it's very easy to pick up. If you're coming from either MATLAB or Python, really don't worry about it too much. It should be fine. So I'll post a bunch of content to help you guys kind of transition from either one of those languages and get ramped up pretty quickly. So that includes like a 45-minute tutorial and then like a cheat sheet. So I'll post all that on Piazza in the next couple of days. And like I've been using Julia for a while, since like pre-version 1.0. So like if you have any questions with like whatsoever like Julia related, like please hit me up.
All right. Thanks, Brian. Yeah, Brian is definitely our resident Julia expert. He's sort of definitely better than me. But yeah, I mean, I came from MATLAB, and for a long time, I basically copy and pasted my MATLAB code into Julia and fixed the handful of errors that would come up. So it's ridiculously similar to MATLAB, at least, you know, the easy stuff. So it shouldn't be too steep of a learning curve. If you've done MATLAB, it's super easy. If you've done Python, it's pretty easy still. There's a few more differences between, it's a lot closer to MATLAB than Python, but like it's really not bad. So as long as you've had experience in one of those or both of those, you'll be totally fine, and it should be pretty easy to pick up. And we're going to give you a lot of template code and stuff like this with the homeworks. So it'll be kind of fill in the blanks. So as long as you know how to do like array math, matrix math using like MATLAB or NumPy, it shouldn't really be a problem. Okay. Anybody else? All right, cool. So I'm now attempting to make my tablet work, and this is a perennial challenge. It is always harder the first time. I haven't done this in a while. So here we go. Share screen, start. All right, I think it's working. Cool. Hooray, we're in business. All right. So, and like I said, yeah, if you have questions while I'm doing this, just speak out, because I'm like off in my own little world here, looking down at things, and I can't see the chat super easily. Okay, so what we're going to talk about today is kind of dynamics. I would say, I guess, continuous time dynamics in particular. Of controlled systems. So hopefully this is a review for most of you guys, and you've all done some of this before. If you haven't, definitely, you know, speak up, talk to us, and we should be able to get you up to speed. Okay, so the most general slash generic form for a smooth dynamical system is the following. So we have a first order vector differential equation that looks like this. So X here is generically called the state. And this is a vector in Rn usually, although we usually make this assumption that it's a vector in Rn, but it's often not. In fact, most of the time in robotics, it's not, but we still kind of assume this in a lot of cases. So that's sort of, you know, positions, velocities, everything you need to describe where your system is and how fast it's going. So for most robots, this would be like, you know, maybe the center of mass position and velocity plus all the joint angles and the joint angle velocities, that kind of thing. So that state, the U here is called the input. And again, this is a vector, usually in a different dimension from, so we say Rm for this guy. And this in most robotic systems, this would be like your joint torques, for example, on an arm or on a humanoid. For a quad rotor, this is like the thrust from your propellers or the motor currents, if you want to go lower level. For rocket, this would be like the thrust and the gimbal angle for the engines, this kind of stuff, right? So this is the stuff you have control over on your control system. And then x dot is actually obviously the derivative of your state. And then this thing f, this f function, we call this function the dynamics. Right. Okay, so that's, I think, all there is to say about that. So for any smooth system, we can always write it in this form. This is super, super generic, right? For a mechanical system, so most robotic systems, the state vector will look like what we call the configuration. So this is kind of position and or joint angles. We call that Q, and then the velocities, V. So this guy is called configuration. This guy's. And in particular, this configuration Q is not always a vector. That's going to be important later. But V is always a vector. Okay, any questions about that? Okay, so we're now going to do everyone's favorite dynamical system, the pendulum. So, I mean, I'm sure everybody's seen a pendulum before. So this is hopefully a super review. So this guy, we're going to do the classic thing. We've got, some mass m over here on the end of it. We've got the length L here, and then we got an angle theta defined like this. And if you do kind of your standard F equals ma torque balance or Euler-Lagrange equation, however you want to do it, you get dynamics that look like this: ml squared theta double dot plus mgl sine theta. And we're going to assume, since we're in a controls class, that we have a control torque here, that we have an input that we can actually do something to the pendulum, right? So we'll say equals tau. So we assume we have a torque about the base of the pendulum, the same angle theta right there. And this torque is going to be, we're going to treat this as our control input u. Okay, so those are our dynamics. And here, right, so looking at our kind of generic form of sort of dynamics there, we're going to put this into that generic form. So to do that, we need to define our configuration and our velocity and kind of stack it up in that standard form. So here, our configuration Q is just theta, the angle, and our velocity V is going to be theta dot. And if we put this together, we get x equals theta dot, and then our dynamics is going to be x dot, which here is equal to theta double dot is equal to, so obviously theta dot, we've already got that in the state vector, so that's super easy. That's just theta dot. And then theta double dot, we're just going to solve this equation in the box for theta double dot and kind of move things over. So we're going to get minus g over L sine theta plus 1 over ml squared u. Okay, any questions about that? So that's pretty straightforward. Everyone's seen this before, I'm hoping. Here's the fun bonus question. So we said, this whole thing about configurations not always being vectors. Does anyone know what the configuration space actually is for the pendulum? It's not R or Rn. Does anyone know? Bonus question.
Depending on how if you're saying there's a ceiling or not, it's sort of, I believe, S1, just
Yeah.
circle.
Excellent. Yeah, so it's a circle, right? I mean, this is very intuitive stuff, but geometrically, it's not the real line, right? And in particular, it's topologically different from the real line because it wraps around on itself, right? So this is actually kind of interesting. It's a compact manifold, as in it wraps around. It doesn't go out to infinity like the real line would. So actually here, the Q is not a vector. It's actually an element of this S1, aka circle. And on that, what's the state space then? So we have the configuration space, or configuration manifold is the circle. What's the state space when I have both configuration and velocity? So
That's a torus.
Yeah. So why is it a torus? Oh no, sorry, it's not. I'm sorry. That's wrong. Sorry, I wasn't listening. So it's not a torus. So remember, okay. So the configuration is a circle. The velocities here are not an angle. The velocities are a vector in Rn. Oh, so in particular here, they're just R, right? So think about circle. The velocity vector is tangent to the circle, right? So it's this tangent line at any point on the circle. So actually, the state space here is actually S1 cross R. It's the circle, and then at every point on the circle, the velocity is just R. So topologically, if you think about that geometrically, what that actually is a cylinder. It's sort of a circle, and then you have, at every point on the circle, you get the real line. So you have two coordinates, and that's the cylinder. These are just fun facts that often don't get talked about, but are, I think, interesting. Okay, and yeah, this guy's at X here. Okay, cool. That was a fun little aside. But yeah, this shows up all over the place. So the torus, someone talked about that. Torus is actually the configuration, not state, configuration manifold for the double pendulum, right? Because there you've got S1 cross S1. So you have two circles, right? The first link and then the second link. And that, if you imagine you have the circle, and then every point on that circle, you have another circle, that makes a torus. Okay, cool. So moving on then, enough random distractions from me. All right, so now we're going to talk about a slightly more sort of specific class of system, or restricted class of system called control affine. Okay, so these look like the following. X dot equals, we're going to call it F naught of X, which importantly, this is only a function of the state, plus, what should we call this? We'll call this d of X times U. So this F naught, we call the drift term. And then this guy is called like the input Jacobian. So we call this control affine because in the control input, U, this is affine, right? It can be totally nonlinear in the state. So like F naught of X can be totally nonlinear, B of X can be totally nonlinear, but B is a matrix, right? And that multiplies U. So in terms of just U, this thing is control affine. And the interesting thing about this, so this has a lot more structure than the first problem, right? And it turns out that most systems can be written this way. In particular, all mechanical systems can be written this way. And I would say, actually, I think any smooth system, basically, you can write this way. And this has some important control implications. So you know, if I have a system that doesn't look like this, there's a trick for rewriting it in this form. I can, so like if I have sort of weird nonlinear coupling between an X and a U, there's a trick, mathematical trick at least, where I basically introduce new states that correspond to my original U, and then I make my new control input the derivative of whatever U was before. And if I do that, it becomes control affine. So there's always mathematical tricks you can play to put not control affine systems into this form, as long as they're smooth and differentiable and all that good stuff. So if we do this to our pendulum, here's what that looks like. So I'll put my pendulum in this form. F naught then is gonna be theta dot up here, no problem. And then the G over L sine theta term. And then this B of X guy is gonna be 0, and then 1 over ML squared down here, right? So it's whatever was multiplying U up top there. Does that make sense to everybody? Okay. So that's that. So next up is one that if you're a robotics person, you've almost certainly seen. If you've taken KDC, I know you've seen it. So this is manipulator dynamics. And this looks like the following. There's several flavors of this that you'll see, but we're going to do this a particular way because that's what our dynamics toolbox that we're going to use, how it does it. So here's what this looks like. This is maybe bad notation overloading on my part, but I don't know. It happens, and this is what people do. So we'll go with this. Okay, so this M guy up here is called the mass matrix. This C guy here is called the dynamics bias, or dynamic bias, or just bias. And this includes, like, for example, your Coriolis terms, your gravity terms. People often wrap damping terms in there as well. And there's a few ways to write this, but this is sort of the one that the toolbox we use in Julia uses, so that's what we're going to do. This thing, once again, is called the input Jacobian. And the rest of this stuff, you know what it is, I think. Cool. Okay, so this is the dynamic stuff, and then often we will also have sort of a second piece of this. So notice this only, this lets us solve for the accelerations, right? So V dot accelerations. We still need to solve for the Qs. So how we get those, we need a second ODE. And that looks like this. And a lot of times we don't talk about this. We will, because it will show up later. And these, we're going to call this the velocity kinematics. So a lot of times the Jacobian in there, that G of Q, is the identity. So a lot of times we have, V equals Q dot, and then this is kind of trivial, and often we don't even bother talking about it, but many, many times that's not the case, and there's sort of a Jacobian in there. And in fact, a lot of times V and Q dot are different dimensions. That happens, for example, we have attitude dynamics going on. Okay, so if we have a system in this form, we can always kind of put it in our kind of more generic form, like so. The velocity stuff is just g of q times v, right? And then the other stuff, we just take that manipulator equation and solve it for v dot. So that we just kind of move everything over. We're going to get minus m of q inverse times b of q u minus c. And I'll leave out the details there, the arguments. Okay, so going back to our pendulum and kind of writing it this way, it's pretty, you can kind of sort of squint at the equations up above and kind of see what these terms are. So m of q here is just ml squared, and you can see this up here, right? So it's the thing multiplying v dot. So our v dot here is theta double dot. So ml squared is the mass matrix, or generalized inertia tensor, if you want to be fancy. The Coriolis term or dynamic bias term here, the C is our is basically the other term there. So GL sine theta. So the other term from up here, right, from this guy. And then what else we have? Right, and then the other stuff's super easy. So then the B here is the identity, and because Q dot equals V here, we're just using theta dot for V. That kinematic Jacobian guy is also the identity. Okay, so any questions about that? All right, and the last note on this is that all mechanical systems, every mechanical system you'll encounter, so pretty much every robot can be written in this form, manipulator form. So this shows up all the time, super useful. Does anyone know why that's true? Take a guess. I know most of you guys have seen this before. So anyone know where this comes from or why this should be true? Like, why can I always do this for a robot? Someone make a guess. No one has any thoughts? Killing me. All right, so this will be, I'll make this a bonus question. If anyone can like work this out, I'll tell you why basically, but then if anyone actually wants to work out the detail, this is worth bonus points. So this manipulator equation, where this comes from, this is actually just a way of rewriting the Euler-Lagrange equation from like Lagrangian mechanics. So in particular, if your Lagrangian equals 1/2 V transpose M of Q V, like the usual MV squared thing, minus like a potential. If you turn the crank on that and just plug it into the Euler-Lagrange equation and simplify it down, you'll get the manipulator equation. So if anyone does that and actually cranks through this, you get bonus points. Cool. Okay. Any questions about anything? All right. So let's see. Now we should talk about linear systems. So we're kind of going from more general to more specific. And this one is basically the bread and butter of control. So there's lots and lots to say about linear systems. And there's entire courses on linear systems. If you really want to get into this field, I highly, highly recommend taking a linear systems theory course at some point. I know there's one in ECE here. So we're not going to go that in depth on these guys, but you should know the basics. So just in case you haven't done a ton of this before, here's the basics. So a linear system looks like this. So x dot equals a times x plus b times u, where a and b are matrices. I put time arguments on them because they're allowed to be, functions of time. There's a few cases here. So the linear system is called time invariant. If a of t equals just a, some constant a, and b of t equals some constant b for all time. It's called time varying otherwise. So if those things do vary in time, it's sort of obvious. There's some other interesting cases you can get into as well. For example, you can have linear periodic systems where like a and b of t are actually periodic with some period, capital T. That can be interesting. That actually shows up a lot in walking systems, for example. So if you're a walking gate, a periodic walking gate, you can end up sort of turning that into a linear periodic system, and there's special properties there that you can take advantage of. These are kind of alluded to, super important in control theory and control design. So they're everywhere. And that's for sort of very practical reasons. These are the only systems we know we always can solve, right? We can always solve linear systems, and that's not true of most other things. And yeah, that's why that's the case. And so because of that, because there's like a whole well-developed theory for these things, we essentially can know everything there is to know about any linear system, right? So we often approximate nonlinear systems with linear ones as follows. So if you've got the generic nonlinear system, x dot equals f of x u, you can linearize this and do a is partial f partial x, right? Take a Jacobian, and b is partial f partial u. And you can do all kinds of fancy things. Obviously, you need to evaluate those derivatives somewhere, right? So you can do this whole bunch of ways. There's all kinds of tricks. But if you can play this game, then you can take advantage of all the standard control results for linear systems and apply them to nonlinear systems. And that is really kind of the name of the game most of the time, is to somehow take your crazy system and smush it into the form of a linear system where we know how to do things. Yeah, one of the sort of founding fathers of control, Art Bryson, who whose name will come up again, had a quote that was in like one of his books somewhere or something called, it was "Be wise, linearize." Okay, cool. So that's sort of, I think, roughly all we'll need for dynamical systems, continuous time dynamical systems. There's a little bit more to talk about. We're going to dig in a little more now to some other stuff, but this is sort of the kinds of systems we'll generally talk about and that you'll need to be aware of. And I can post some references on this stuff after. Okay, questions, speak up anytime. Okay, so what we're going to talk about now are equilibria. So this is again, a pretty core concept in control. And so the intuition for what this is, it's a point where a system will sort of remain at rest. And can anyone tell me what that looks like in terms of the dynamics, in terms of f of x, u? Come on.
When it equals 0.
Yeah, thanks. Okay, so that's right. So, remain at rest, not move. So, intuitively, then the derivative here needs to be 0. That's the definition of an equilibrium point. So algebraically, we can kind of just look at this as a root finding problem. I just need to solve f of xu for 0. And if I can do that, if I can find a 0 of that function, I've got an equilibrium point. All right, so let's go back to our pendulum again. So if we write those dynamics down one more time, we've got theta dot, then minus g over L sine theta. So this will just deal with the uncontrolled dynamics for now. And we want to set this all equal to 0. So the top part's easy, theta dot equals 0, velocity 0. That's sort of a no-brainer. How about theta? What does theta need to be here for this to have an equilibrium point? This is pretty intuitive also.
Pi over 2.
So it depends how you define your angles, right? So the way I defined them before in the picture, this is theta equals 0. Right, so sine theta, sine theta, sine of 0 is 0, right? And there's one more. So where else does sine theta equal 0? So that would be straight up, right, pi. So we got 0 and pi. So there's kind of 2 equilibria here. Okay, so now we're gonna do our first control problem. So now I'm gonna look at this with the control torque in there. Okay, so question, can I move the equilibrium points? So what do you think? Can I, so here's yeah.
We can by applying some input.
Yeah, that's exactly right. So what I'm gonna ask now is let's try to put it at say pi over 2. Let's try to put it straight out here. So now I'm going to write the dynamics with the torque input. And we'll take a look. So here we've got theta dot, which we want to be 0, and we've got minus g over L sine. So we'll put pi over 2 in here. And then we've got the input torque. So we need this whole thing to be 0, right? So velocity is easy, but I need to solve that second equation now for 0, right? So if I kind of just go ahead and do that, I get 1 over ml squared u equals g over L sine pi over 2. Pi over 2 is obviously sine pi over 2 is 1. So this tells me that u equals mgl. And so, I mean, this is super intuitive, right? I'm basically applying a torque that's going to cancel out gravity at that position, right? I could make this wherever I want, right? So with this trick, I can plug in any theta I want, solve that equation for u, and get an equilibrium and move it anywhere I feel like, right? So
I have a quick question.
Yeah.
So in this case, the interpretation of this would be that, like, if let's say the pendulum was at theta equals pi over 2 already, and then you wanted to hold it there, then you'd have to apply this u, but it wouldn't necessarily get you to that equilibrium position.
That's right. So what this is saying is, if I want this other point to be in equilibrium, to be a place where the system will hang out if it starts there, this is what I need to do, right? It doesn't say anything about how you get it from some arbitrary point to there. That's sort of, yeah, we're going to talk about that for sure. But yeah, this is kind of one of the core ideas. It's like, if I want to drive a system to a set point, right? First, I need to know what the set point is. And I may need to do some weird stuff to create a set point that I like to drive it to, right? Cool. So in general, right, we can just solve a root finding problem here in U. So given some, X star that I want to be an equilibrium, I can plug that in to the dynamics, set that equal to 0, and just solve for the U that makes that happen. I can't always do that. It depends on the dynamics of the system. For the pendulum, I can always do it. In general, if the system's fully actuated, i.e. I have as many control inputs as I have degrees of freedom, I can do this pretty much. It gets more complicated for under-actuated systems. Okay, so that's equilibrium point, or equilibria is the plural. So the next thing to talk about is stability of equilibria. And this is kind of starting to follow up on the question that was just asked about, like, how do you get there, etc. Okay, so the idea we want to get at here is if we start out near an equilibrium point, will we stay near it under, say, small perturbations? So that's kind of the question. When will we stay sort of fuzzy near an equilibrium point, say under like small perturbations? And to get at this, we're going to look at a super simple 1D dynamical system. It will be a nonlinear system, but a 1D system. And here I mean 1D, the state space is 1D. So the pendulum, it has 1 degree of freedom. The configuration space is 1D, but the state space there is actually 2D, right? Because the state has theta and theta dot. Here I mean the state is 1D. So these are kind of interesting in that we can basically understand everything there is to understand about 1D nonlinear systems, which is kind of cool. So here's I'm going to draw a 1D nonlinear system where the x-axis is going to be x, and the sort of vertical axis here is going to be x dot, which is our dynamics, right? F of x. And here there's no control. It's just an autonomous system. And I'm going to draw sort of the dynamics function. Let's say it looks sort of like a cubic, maybe looks like this. So let's say that's our dynamics function. You can think of this like some weirdo, cubic polynomial or something like that. So first question is, where are the equilibrium points?
The 3 0 crossings.
Yeah, wherever it crosses 0.
Yeah, exactly. So we got 3 equilibrium points at these 0 crossings. So next question, let's look at the one at the origin here. So, and keep in mind, right, like x dot's the vertical sort of axis. So if I get pushed a little tiny bit to the right in this picture, x dot is negative. That means I'm gonna sort of drift back towards the equilibrium point, right? So I'll draw this. So if I get pushed a little bit to the right, I'm gonna end up getting, the dynamics are gonna naturally nudge me back to the left, and vice versa. If I get pushed a little bit to the right, x dot's positive, and I'm gonna get pushed back. If I get pushed to the left, if I get perturbed towards the left, the dynamics will naturally push me back to the right. So I'm gonna sort of naturally stay in the neighborhood of this equilibrium point. So let's go look at one of the other ones now. So let's take the right one, for example. So in this case, if I get pushed to the left, x dot is negative. That means I'm going to go further to the left. Vice versa, if I get pushed to the right, x dot's positive. I'm going to go further to the right. The dynamics are going to carry me sort of farther away. And then same thing on the left one. If I get pushed left, I'm going left. If I get pushed right, I'm going right. So looking at this, very intuitively, we say the middle one here, we say this guy is stable because under small perturbations, the dynamics will sort of naturally kind of restore me towards the equilibrium point. And then the other two, we say are unstable, because if I get nudged a tiny bit away from the equilibrium point, that's it, I'm going. Okay, so any questions about that? Does that make sense to everybody? Cool. So we're going to now sort of like take this really intuitive picture and we're going to kind of generalize it to n dimensions almost trivially. So what we're going to do is look at the slope of f of x, right? So what we kind of did here is we reasoned about is x dot positive or negative on either side. And we found, you know, how this works. So if we look at the slope now of f of x in the neighborhood of the equilibrium point, you'll notice in the stable case, the slope is negative. So partial f, partial x, negative implies that the equilibrium point is stable. And conversely, if you look at the unstable cases, the slope at the equilibrium point is positive. And that implies that if you have partial f, partial x positive, you're going to be unstable. Your equilibrium is going to be unstable. So that's coming just right from this picture that we just did. In higher dimensions, we can still take these derivatives, but they're no longer scalars, they're just Jacobian matrices, right? So what do you think happens in higher dimensions? So we get partial f, partial x. This is a Jacobian matrix. And so it's n by n, where n is the state dimension. So it's a square matrix. And
does it depend on the semi-definiteness?
No, so that sort of property, that's for a quadratic form, right? So that's a symmetric matrix. We can talk about definiteness. This is not necessarily a symmetric matrix. This is just the Jacobian matrix of some random dynamics function. So this, we can't really say anything about the definiteness of this matrix. And it's not a quadratic form, so that's sort of not the right thing to talk about. It's a linear map, a linear function. So what we're actually going to do is we're going to take the square matrix and we can do an eigen decomposition of it, right? And what that's really doing is decoupling this system into n one-dimensional systems, right? So if you think about an eigen decomposition sort of geometrically, what it's doing is finding you a coordinate transformation such that that matrix is diagonal. And in this context, what that means is we're finding some funky coordinate transformations such that I've decoupled all of the degrees of freedom of this system, and I basically just have n one-dimensional systems. And once I do that, I'm in exactly this place again that I just drew the picture for. So the eigen decomposition is basically a trick for finding a clever coordinate transformation that puts us back in this 1D picture, and then we can apply the 1D result. So this sort of decouples us into n1D systems. And then we, the n1D systems, right, the eigenvalues are the diagonal elements of that, that matrix, and those are kind of telling us what each 1D system is doing. And we can look at the real parts of those eigenvalues, it turns out. So we'll write it like this. So I take this eigen decomposition of my Jacobian, I look at the real parts of the eigenvalues. If they're all negative, this is saying like all n of those little decoupled 1D systems is stable. So then we can say that the whole system is stable. And otherwise, it's unstable. There's some subtlety in here, but practically speaking, that's sort of what you want to look out for. Any questions about that? I know I did that kind of quick. I expect that most of you have seen this before. If you haven't seen this before, just send me a ping and I can shoot you some stuff to read, or we can talk more about it in office hours. But should be, if there's any questions though, don't hesitate to speak out. Okay, so now we're gonna do this for the pendulum. And the result should not be surprising. So we got our f of x theta dot minus g over L sine theta. I can take the Jacobian of this, partial f, partial x. This is going to be a 2x2 matrix, right? And that matrix, I'm just going to do this real quick by hand. So I do the first row, I take partial the first row with respect to theta, 0. Partial the first row with respect to theta dot, 1. Then we do the bottom row, partial with respect to theta is derivative of sine is cosine, so it's minus g over L cos theta. And then partial the bottom row with respect to theta dot is 0. So I get this. And yeah, just kind of following on to that the previous question about like positive definiteness, this is definitely not symmetric, right? So they're sort of not, sort of weird to talk about definiteness in that way for something like this. Okay, so now we've got our Jacobian, and all we have to do is evaluate it at the equilibrium points that we want to check out. So let's look at the top one first. So we do partial f, partial x, evaluated at theta equals pi. If we plug that in, we get 0, 1, g over L, 0. I can take the eigenvalues of this guy, and this for 2x2, it's pretty easy to do by hand or with a calculator. I'll spare you the in this case, it turns out this is plus or minus root g over L. And we check the signs on these guys, right? So obviously, this guy has a single positive eigenvalue and a single negative eigenvalue. And then because of that, the positive eigenvalue means that we're unstable. So if we do the same thing for the other case, we're gonna get a minus sign down here. And if I take the eigenvalues of this guy, it turns out what I'm gonna get is plus or minus I or j, depending on your persuasion, root g over L. And so this is pure imaginary, no real part. This is a bit of a weird case that we didn't talk about, but now we're going to talk about it. So sort of in the theory of linear systems, we call this pure imaginary case marginally stable. Does anyone know what this means, like physically, for the pendulum?
No friction, it just keeps going back and forth.
Yeah, it means that there's no damping in the system, and that essentially pure imaginary eigenvalues correspond to oscillations, right? So this kind of means you basically have undamped oscillations and that things are just going to oscillate forever. But there's a catch to this. So this is true in the linear case, in the linear systems case, but if we're doing this, if we're applying this linear analysis to a nonlinear system, what this means is that there's going to be higher order terms in the Taylor expansion that we're ignoring right here. And if you've got, if the first derivatives here, these eigenvalues, if these have 0 real part, you can have these oscillations, but you've got the nonlinear terms in there too, and kind of all bets are off on those. So for a linear system, you have this sort of marginally stable, undamped oscillations kind of thing. But if you're doing this on a nonlinear system, this is sketchy and you can't really trust it. It turns out for the pendulum here, which is a nonlinear system, it turns out it really is kind of this pure oscillatory motion thing, but in general, if you have a nonlinear system and this happens, you can't trust the result, and you basically want to be very careful and or assume it's unstable. As just a last comment on this, if we add damping to the system, which we can definitely do with our control input, right? So if I, for example, wrote down a feedback controller and I set u equal to minus, say, kd times theta dot, which is the equation for a damper. If I added this to the dynamics and then redid this analysis and computed the eigenvalues again, this would give this pure imaginary case, would give it a negative real part and would make it stable. Okay, so that's time, guys. Sorry, a little over there. I'm happy to hang out for a little bit if anyone has questions. Otherwise, join the piazza, and we'll see you guys on Thursday. Thanks, everybody.
Thanks, Zach.